Good evening and welcome to Tinkering with Atkelar. In this episode, I got another vintage HP device. I was looking for one of these old school counters for quite some time and finally found a decent buy it now offer on eBay. So what is this 5512A exactly? It is a digital counter, which means it counts digitally. Sorta. You see, these devices can be seen as the granddaddies of all frequency counters. The idea is to have a set time period and count the number of pulses on a signal within that period. So if you take 1 second and count 100 periods, it is of course 100 Hertz, or 100 cycles. This device is from around the time the term shifted from cycles to Hertz, as I've seen both used in the manual. To achieve the required high counting speed and accuracy, this device uses flip-flops for dividers and Nixie tubes for a display. I'll get a bit into the circuit later on. Overall, the look of the device isn't all that bad, a bit scuffed up on the case, but the front panel is looking quite good. The inside is organized into several PCBs, connected on a backplane. Which itself is just a bunch of wires. Note that high voltage warning. They are not kidding. The plus-minus 150 volt rails are amongst the blank wires on the backplane, so it's almost like a flycatcher. Somebody has hacked a power cord into the device with some cheap screw terminals. I know that these old oval-style power connectors are a pain to find these days, so I'll modify that to a regular ICE connector instead. Like usual, I try to remove the more fragile parts first, in this case, clearly, the Nixie tube assemblies, but they wouldn't come out. Again, I don't want to use too much force either. And so I removed the bracket part that holds them together and took out all of them at once. Had to remove part of the front panel to get it to move, and there's also a wire running across. The rest of the boards come out just fine. The case looks like there should be a fan, but there isn't. A peek into the service manual confirms it should have one indeed. Taking apart the case next, there is some solder joints to undo and the back panel has, again, a voltage selection switch riveted to it. Since I have to mod the power socket anyway, I just drill out the rivets. Now to the recapping. I wanted to do my best to keep the looks of the old filter caps intact, so I gutted them and put in the new ones. And yes, since I now have a leakage tester, I did try them. One was completely gone, the tester didn't even see a slow charging. The others were still quite slow to charge, definitely needed replacement. The PCBs also had some electrolytics and one tantalum on them. Business as usual. I cleaned all the potentiometers and switches again. The power switch is a bit weird. It has no contact points. It just slams a copper piece against other copper pieces. I wonder how that ages. Did they chew out the hole for the power cord mod? Sheesh, that's not a burr, that's a growth. The back panel mod goes okay. No need to be 100% accurate, the socket has a lip to cover up any irregularities, but at least I do some deburring. After a good clean of the backplane, I start to reassemble. First, the transformer and input amplifier bracket. Those dangle in their connecting wires a bit too much for my taste, so I want them to be fixed up ASAP. I'm covering up the power cord mod with a grommet. The digital printer output is specifically designed for an automated numeric printer that HP sold. Think of cash register or tabletop calculator style printers with spinning number wheels. After finishing up all the wiring again, I turn on the transformer and check the voltages. Looks good. Up next, the power supply module. I'm trying to dial in the -35 volts, but it's not changing no matter how much I twiddle the knob. Must need some load then. So I put the pot back to the center position and populate all the other PCBs. And now it works. -35 volts set. Also, the Nixies are all working, at least the digits I can see for now. Up next is a quick function check. The input sensitivity dial has a latched position for testing. This will put the internal clock to the input, so the display should read all zeros and a single one, except in the two fastest ranges. The counter mode will count in 10 Hz too. The reference frequency is a 100 kHz quartz signal, but there's a trim cap near the rear to tune that. It can even be tuned without opening the case. The external clock input turns into an internal clock output when the internal clock is selected. So I use my digital scope to get it as close to 100 kHz as possible. And now, testing, feeding in a sine wave from my generator and checking the display. And after quite a bit of searching, I found a fan that fits into the case. A quickly made set of 3D printed brackets later, it's all ready to keep the tubes and transistors cool again. And last but not least, some new feed. Also a quick 3D print. Add a bit of rubber buffer material and it's all ready to go. Almost as good as new. The counter has two general modes, frequency and period. Switching between those will basically trade the input signal and the reference clock, so it's either periods per time or time per period. And here's an overview of the circuitry. The input signal is amplified and fed into a Schmitt trigger. This makes sure that we get a clean rectangle signal out of the input stage, no matter what style of signal we feed into it. The reference clock is generated on another board and distributed within the case. Both the clock and input signals are switched around with the range switch. Depending on the selection, the signals are routed to several divide by 10 stages. Note that this is a digital counter, but not a binary one. It doesn't use the 1, 2, 4, 8 values for the bits in a stage, but rather 1, 2, 2, 4, so you can have bit combinations that represent 0 to 9 only. The result of the divider stages is fed into the first Nixie counter module, which overflows into the input of the next one, and so on. Thus, each Nixie counter is also a divide by 10 for the next stage. These are also the 1, 2, 2, 4 logic and have an interesting optocoupler-like way of transferring the bits to the Nixies. Essentially a demultiplexer, but with neon tubes and light-depending resistors. Nixies are, essentially, neon bulbs with designer filaments. So they need a good DC voltage to get the glow going. Usually I see about 150 to 200 volts for that. The transistors run on minus 35 volts for the logic levels. And yes, there is not a single integrated circuit in this device. The trigger, gate and reset circuitry is handled by the remaining two boards. The last mode is called manual, which just counts pulses until the stop mode is selected. That makes it sort of a monitoring tool, useful to count events like button pushes in a test rig. Now these counters have a slight problem with exact numbers. Since the gate time, i.e. the time that the counter actually counts, is not synchronized with the input signal, it can easily display ±1 without being wrong. That's why the tolerance always includes ±1. And that's it for this episode. I hope you enjoyed this vintage counter. See you next time for something very special. Automated numeric printer that HP sold. I think those catch registers. Yes, catch register.